All right, as Professor Saylor mentioned, my name is Matt Groves. I've worked in industry, instrumentation, ventilation for quite a few years. I came back part-time to work on my master's here, and so I have about one class left and trying to graduate this term. So currently work for Zender, who makes HRVs. We'll talk about later or throughout this. And as Professor Saylor said, I'm a certified passive house consultant. So a couple of years ago, I found out about this, got interested in it, and got certified to do design. The three basic overall requirements for the performance standard are the first one's a very airtight envelope. So most people know about blower door tests, understand them. So you depressurize the house, so you put a big fan in the door, depressurize the house to 50 pascals for new construction or just for checking buildings. And then you measure how much air is actually flowing out. So it's actually how much air is infiltrating through the walls, cracks, and monitoring. So they have a requirement of 0.6. And probably most normal houses have somewhere 5 to 10. Newer high-efficiency homes are getting under 5. So this is a very tight house, and we'll talk more about that. Then I also put up the natural. So they tested at 50 pascals, so that's much above the wind pressure. So when you're testing, if the wind's blowing a little bit, it doesn't affect you're above what ventilation would or infiltration would be caused by the wind. So you can say the wind is almost negligible unless it's really hard. And then there's been studies. Lawrence Berkeley Labs back in the 80s did a study trying to say, well, if you tested at 50, what's really the natural ventilation infiltration rate? So that just the house, how much air is coming into the house. And you have to look at, they have a whole map, a geographic area, and then you look at how much exposure, if it's a 1-story, 2-story, if it's really exposed to the wind, those types of things. And they came out with what's called the N factor. So you divide that into the number you get for into the ACH 50. So in this case, it's about 20. It could range from somewhere 15 or 17 up to 23. But somewhere in the average is 20. So if you divide 20 by that 0.06, you get that 0.03. So that's just showing how much, if the house is sitting, how much air movement is in the house if nothing else was happening, which is pretty low. Like I said, most houses leak quite a bit. And then the second one, and we can talk more about that, the second one is specific heat. So that's just what it takes to heat the house, how much energy. And they just have this maximum requirement of 15 kilowatt hours per square meter of floor space per year or per annual. And that's about 1.4 kilowatt hours per square foot or 4.75 kilobtu's. So that's just telling you how much maximum heat the house can use during the whole year, which is quite low. And then the total building primary energy, where they're considering the whole energy the house takes. Because once you reduce the heating load and cooling load, where you have a cooling load, then you're left, the next biggest user is usually hot water, and then other devices, and if you have really energy hog plasma TVs, those really might use more energy than your heating system. So they look at the total energy too. So, and then they use their passive house planning package, which is this Excel-based energy modeling that they've developed over quite a few years and actually tested it against built houses and perfected it to do the certification. So you need to put all your parameters in that program, and then it'll figure out if you're meeting these requirements.
Question, what's the A after the meter squared?
Yeah, that's annual, or that's how but it's per year.
Okay.
Yeah, and just ask questions as we go along. And like I said, this is the passive house. When it's translated into English, it's passive house, and some people get that mixed up with solar passive. So this house tries to act on all the passive elements versus the active elements. So it's really putting a lot of emphasis in the building envelope. So really good walls, good windows, and minimizing the active systems in the house required to provide the heat and the comfort. But it is trying to orientate and use some passive solar gains, but it's not, you wouldn't say it's the same as the passive solar. Passive solar is looking at just pure solar coming in, looking at the mass of storage and things like that. So here, I was trying to see if this is still current. I did this a couple of years ago, but if you kind of just rated the average American house, so all the old houses and new houses together are somewhere around 130 kilowatt hours, and this is for just the heating energy, somewhere around that. And if you build it to current codes, you'd be around 100. And then LEED and Energy Star at the time you were improving it by about 15%, so that'd be about 85. I think LEED might be better now. Passive house would be down here, and then net zero, of course, would be 0. Net zero meaning over the whole year, where you're probably using more energy than you're producing during the winter, but then making it up in the summer. So that kind of shows you kind of where everything lies. You'll hear about other house standards out there. There's one called Minergy, which is minimum energy, comes from Switzerland. There's a Living Building Challenge, which is emphasizing the sustainability aspect, but also looks at net zero. So quite a few others. And just looking at what really makes a passive house, the key element, like I said, is basically the envelope. So you see the super insulated envelope, air barrier, and you're trying to orientate it to use solar gains from the south, so you got the sun coming in, but you're using really high efficiency windows, so you're not losing much heating energy. And then you have what's called an HRV that's bringing in fresh air. So back in the 70s, people here in the US and Canada were building really super insulated houses in response to the first energy crisis back then, when energy kind of jumped in price. And they built really super insulated houses, but they were not well ventilated. So they kind of had a toxic inside to them. So people kind of shied away from those. And then when energy prices got high in Europe, as they were, guys from there looked at what the U.S. had done and other people were doing, and developed an HRV, which is actually recovering the heat. And we'll talk more about that. But here it shows the inlet to it is going, say it's below freezing outside. It's actually trying to warm up the airflow through the ground first. In our systems, we just do a ground loop where the air never goes into a earth tube, because in certain moist climates, you might get condensation down there, and not the most hygienic, because you want that your fresh air. So other systems like the one we have, they just run a loop, like a PEX loop in the ground, circulates water glycol, and that'll circulate through a hydronic coil, and the incoming air will go through the hydronic coil, and the pump for that hydronic coil will only run when it's necessary for heating. For example, if the air is negative 20 degrees outside, your ground temperature is usually 45 or so. It'll warm it up to near freezing, and then you don't have to do an electric preheater. People also use electric preheaters, but when you're trying to do near net zero, that uses a lot of energy. So we'll talk about that a little bit more too, but I just wanted to point this out, where you might see a lot of people talk about earth tubes. They can work in dry climates, but you have to be careful not to collect moisture in there, because like I said, you want to be breathing the most fresh air possible. And then it shows that the supply, it's putting that fresh air to the bedrooms and living spaces, and it's extracting from the bathrooms and kitchen areas. So that's kind of the general process there. So what does a passive house look like? This one is in Portland. It's a house I worked on a little bit. The guy had a 1998 house, just stock, 2x6 walls. He said, I want to really look at reducing my energy needs, and I'm going to live there for probably forever. So what he looked at possible ways to increase the envelope first. So for super insulation, airtight, and he decided he didn't want to use a lot of rigid foam, so he went with walls with cellulose. So what he did is tacked on what's called Larson trusses. I tried to take a picture of there on the side. It's just taking taking the siding off the house, going down to the sheathing, and then putting these beams, or they're just 2x2s with 10x10 plates of plywood to just extend the wall out so you can fill those spaces with cellulose. And he got up to probably a R50 wall around the outside. And that's just onto the existing. So he didn't have to take the existing sheathing off, but he had to seal the existing sheathing and do some more work. But so that's here. Here's one in California worked on, Menlo Park, and it's just a SIP, structural insulated panels. So they're just EPS sandwiched by 2 sheets of OSB. And you can order different widths and pretty high ceiling. And is the screen good with the lighting? Is this good, or should we get to everyone? I'm seeing you here. Okay. So this is one house, like I said, in California. In California, they have less heating loads, heating degree days, so they don't have to insulate as much to meet the code. Here's another one in Portland. This had double stud walls, plus 3 inches of rigid on the outside to meet the requirement. And this one was done by the same guys who built the truck house. Their truck house was the next project. I don't know if Professor Saylor has talked about the truck house project or the 2 duplex projects. So, and then even up in Alaska. So this house was, the guy wanted to build it and try to get the best net zero. So he wants to be net zero fossil fuel. He still burns a little wood in the winter, but he's actually built a house, and it's so far north you can see the angle of the solar panels. Usually they're about the same as your longitude. So here it's around 45 degrees. You'd be somewhere 30 to 45 degrees up there. He's so far north, they're almost vertical. So those are just the solar thermal for his hot water system. He's doing a radiant floor system. He's got RHRV in there, and then he's got the ground loop. So even when, this is Fairbanks, so it's much colder than Anchorage. So even when it's negative 50 outside, and the ground temperature might be, even though it's permafrost near freezing, it'll still warm it up from negative 50 close to freezing, and that'll be enough so the HRV doesn't have frost issues and get that air in there. The other thing you'll notice, he's got these panels, the window coverings, external window shades that he can roll, and it has insulation on them, so it protects and reduces the amount of heat escaping during the winters. And since they're an area where I think they have at least quite a few days where they have less than an hour of sunlight, they use those to help insulate the house. So they're movable window shades, external window shades. And then a couple from Germany I show. This is, and it's not just residential, it's commercial, multifamily. Most of the houses in the U.S. have been residential, but there's lots of schools in Europe, and also multifamily houses in Europe that meet this standard. And they started a long time ago, and because their energy prices, when you look at their energy prices, like people talk about, I was in a group where they were talking about different energy prices, and the guy from France, they were saying, hey, those guys only have pay 8 cents a kilowatt hour, and that's 8 cents euro, because they have mostly nuclear power, where Netherlands were paying around 22 cents euro, and then we pay here about 8 cents, which is about the same as 6 cents euro. So comparing a lot of Europe paying 22 to us paying 6 cents, there's a lot more incentive for them to build energy efficient. So that's why it's kind of taken off since the 80s there, and we've had relatively cheap energy prices. But if our prices were 3 to 4 times as much as they are now, like they are in Europe, probably more people would be focused on reducing the amount of energy homes and houses take.
Do you know what rough paybacks are for retrofits and new construction?
Yeah, new construction, it's less expensive. Retrofits, it takes more because you're actually, it costs more to first deconstruct and then reconstruct. But if you're only paying, say, I don't know, most people, it depends on how leaky your house is. Say you're paying $800 in just heating costs, and it costs you, $35,000 extra for a new house. It's going to take quite a few years, but that's assuming what the energy prices are now. So you have to look at how much energy prices are going to rise. Everything. The main costs of these are in the windows. There's a little bit of extra labor, and we'll talk about how your heating system really goes down in price. But the main extra cost is windows. But if you do have an older house that needs siding and windows, you can pull that off, replace the windows, seal the outside, and do some other things, and it starts making sense when you do that. But if you're going to take a house that has decent windows in it now, let's say double pane, it gets more costly. And then the labor it takes to try to seal everything. You can get close, but just air sealing a leaky house, especially the old ones that are like story and a halves with knee walls, and they get pretty complicated to seal, air seal. So a little bit of history on the passive house. Like I mentioned, it started here actually in the 1970s. We were super insulating houses. This one Harvard physicist wrote some work or did some studies on it and wrote some papers on super insulated double envelope homes. And then a couple guys from Europe looked at that, took some of that work, and started developing the passive house. One was Bo Adamson and then Wolfgang Feist of Germany. So in 1996, they started the Passive House Institute. And then by 2005, it says 5,000 passive homes in Europe and 15,000 worldwide by 2008. So it started small. It's kind of growing as people want to really build and focus on energy-efficient homes. And then here, a German architect saw what they were doing, brought it over to U.S., built her own house, and then started the Passive House U.S. in 2007, and they currently certify homes. There's some discussion where there's other Passive House members that are from different countries also certifying houses here. One's from called the Passive House Academy. So there's some discussion there, and there was a discussion with the U.S. group on trying to relax some of the standards because it's harder to build in the north, a passive house, and so they were going to change it, and the Germans said, one standard, and they said if you're going to change the standard, change the name, and so there's been some discussion about there, but right now it's the Passive House Institute is the one certifying the homes. Yeah.
Are there lower air standards and lower temperature requirements in a passive house? For example, the standard temperature range should be like whatever it is, 68, 72 winter, summer. Does it get a wider range allowance?
Slightly, but they usually design for heating to 68, which is 20 degrees C, so they just say 20 degrees. But a lot of the heat from a passive house is given off by people, appliances, solar. So they're not designing the systems to heat as much. They're relying a lot on the passive energy from the house. But it's pretty much the same comfort. You want the comfort, but the keys in a passive house is that because it's super insulated windows and walls, the temperature against the wall of an exterior wall is within 2 to 3 degrees of an interior wall, or the temperature of a window. Say, in a regular house, you're sitting close to a window, and you're feeling the cold radiation off it. You're actually feeling colder than it is in the house. But in a passive home, you're not feeling as cold because that window, the inside window temperature is within 2 to 3 degrees of probably the whole house. So for thermal comfort, it's a much different feeling. And also for heating systems, we'll talk about, but most conventional houses, they put the registers near the window because that's a cold spot, so they don't want cold spot, but then the hot air will hit the window and actually you'll lose a lot of heat out the window that way. But here you can actually put the register near the inner wall because it'll just kind of move around and not lose so much and not feel the cold out towards the outer part of the window. So some of the principles talked about: super insulated envelope. You're reducing, eliminating thermal bridging. Like with regular walls, you have the 2x4s or metal studs where even though your wall might say it's R21, it's really R21 only where the insulation is. Where the studs are, it's leaking more. High performance windows, talked about airtight construction. We'll talk later about the heat recovery. And compact and simple building shape. This just says if you're going to, a 2-story rectangular house is compact. Say you got a 2,000 square foot home and you have a 2-story, 1,000 square feet on each story. That's much less external surface area than if you just had a 2,000 square foot single floor, one floor. Because you think of the roof and the floor on that single story as being 2,000 square feet each, where on this 2-story, they're only 1,000 square feet each with a little extra wall space. So when you do that, that's why you're looking at compact. So a lot of these cut-up houses with really all these wings, they're just kind of adding more heat loss. So they try to make them compact. The most compact would be a cube, but they still want some good aesthetics. So the houses can make them good, but depends on how much you build the walls thick and everything. And another thing about the passive house is kind of it's a more systematic approach where you're looking, before you actually build the house, you're looking at how you're building the walls, the insulation value, the windows, the heating, the floors, the ceiling, or the roof, and looking and trying to meet the goal by integrating that whole design, where normally a builder will go out and just hire a mechanical or HVAC company to come in and install the heating system, with what they think. They'll hire some people to install the windows, but no one really they just kind of ballpark it, and no one's really looking at the overall energy picture as you're building the house. You just, most time the HVAC contractor will oversize the system because he doesn't want callbacks. So the best way not to get callbacks is oversize the system a little bit, but that also creates inefficiencies. So here you're looking really nailing down and saying, how much heat load do I have? What do I need the windows and walls to be to work together to meet these energy requirements? We talked about the passive, so you are trying to use passive solar. Minimal space heating. You want all ducting inside the thermal envelope. A lot of houses nowadays, if you look up in the attic, you got duct runs up there, duct runs in the crawl space, all losing heat. For Oregon high-performance homes, those have to be inside the thermal envelope, so they are changing codes slowly to kind of look at energy wastefulness and trying to improve those. And then energy efficient appliances. Yeah.
If most of the energy is produced passively by people and appliances within the house, then how is the energy contained in the house if you need to do ventilation, bring new air from the outside?
Yeah.
If you just keep bathrooms real cold wherever you're returning the air so that most of the energy is contained within the living space?
Yeah, that's a great question. Got more slides on that. But the main thing is on a heat recovery ventilator. So currently most houses just have bathroom exhausts and kitchen exhausts. So when you turn the bathroom fan on, all that's, if inside 70 degrees, all that 70-degree air is just going outside, and it's sucking the makeup air through the walls and cracks of your ceiling and walls, and that's probably not the best air you want to breathe, coming through old insulation and all that. So you're losing all that heat. So this is a balanced mechanical system where the same amount of air you're exhausting, you're bringing in. So you're balancing so there's not a negative pressure in the house. But also when you're exhausting the air, you're going through a heat exchanger. So that's where the heat recovery part comes from. So say it's 70 degrees you're exhausting and you're bringing in 40 degrees and you're going, it depends on the type of HRV, but say it's a cross flow, or a counterflow, where it enters in at 70 and then this other side 40. So by the time the 40 degrees exits, it's up to within 2 to 3 degrees of the exhaust temperature, or within 2 to 3 degrees of 70 degrees. So you're up to 67 or 68 degrees of the air you're bringing in. But that's the 90% HRV efficiency, which we talked about. But that's the main thing. And so actually when you're using the bathroom and you're heating and you're taking a shower, the HRV will actually capture, because all that air is going back to the HRV on a continuous basis, and it's actually capturing that heat and putting it into the incoming air. So the air streams never mix. They just, one gives off the heat to the other. So you're getting a constant fresh air, supply of fresh air. We usually try to get about 1/3 of an air change an hour, which is more than a lot of houses get, but it's fresh and heated, so you're not having to reheat it. And it's within 2 to 3 degrees of room temperature. Yeah.
Do you have to leave like fans on for extended periods of time to get sort of all the moisture from the showers?
Yeah, these systems we're talking about run continuously.
Oh, okay.
But they're only using 30 watts of power, so less than a kilowatt hour a day, which would be about 8 cents, but somewhere in the 800 watt hour per day range.
So there's generally no moisture problem?
No, it's actually, because it stays fresh and it's constant. We have some houses that actually put what are called towel radiators in the bathroom, just so some people like a warm towel, and it lessens the amount of times you have to wash it since it's clean. But that towel radiator will give off heat, get the bathroom up to 72 or whatever, but all that heat will be recirculated to the HRV, recaptured, or 90% of it will be recaptured and sent throughout the house. So instead of just taking that heat, exhausting it through a regular exhaust system, you're recapturing the heat on that. All right, so here this shows a non-passive house, or actually the house they retrofitted before they retrofitted it, showing thermal bridging. So you can see all the studs, you can see the trusses going across, and then along the ceiling there are top plates. Along the corner you usually have 3 stud corners. So when you're talking about thermal bridging, those are the areas that are really letting the heat out, or bridging between the inside and the outside. For high performance windows, the building in the foreground has high performance windows. You see the heat not much reflecting, where a common normal building is behind it, and a lot of heat. The hottest parts are the windows. You usually lose most of your heat through the windows, and then the walls. So it kind of just compares a passive house with high performance windows to a non-passive house, just a standard. Some of the window specs I just pulled off. This is just an example of a couple of manufacturers. One's called Serious Windows. They have a few grades of window. Well, I did 2 of the 925s. Most window manufacturers try to make one window for the whole U.S. So because the southern half of the U.S. needs less sun, and they try to prevent the sun getting in, heating up the house, you usually see the solar heat gain coefficients pretty low. So when you're building a passive house, you want good solar heat gain on the south windows, and if you have any windows on the north, you try to minimize the northern windows. But if you do have northern windows, you want to really a good U value, and you don't really care about solar heat gain because you don't have much over there. So it just kind of shows the two. This one we would put on the south window because it has a high solar, but you really want solar heat gains over 0.5, over 50% of the heat coming from the sun getting through, while at the same time you want a good U value. So right now there's not as many options as you'd like. So that's one of the only problems, is trying to source windows for passive homes in the U.S. Yeah. There's another one I couldn't find the specs on, like Unilux, and there's quite a few others that are coming. So these will only be a couple. So yeah, so there are better windows. This will just be a sample. But you see that a normal window that's installed currently probably has a U of 0.33, 0.30, which would be R value. 1 over that would be 3. So say the new most new construction is putting R3 windows in. Single pane would be R1, and these are, you know, around the R7, R8 for fixed, and then it goes probably down one or two when for casement. And then the European windows are what they call tilt and turn. So you turn them and they kind of tilt inward. For security reasons, if you just want airflow and you don't worry about people trying to break in, the window only tilts in, so people can't break in. That's because most open windows, the type you see most commonly, you can just pull the screen out and break in. But also there's cam locks around them, so the casement windows close the tightest along with these tilt and turns. The sliders have a lot of leakage path where the window slides past each other. So usually if you want a very airtight building, you got to go with either casements or the tilt and turn to get a tight ceiling window. But in our climate for a passive house, you want something around the 0.15 U range, and like I said, on the south, you want good solar heat gain coming in.
Are those U.S. units or?
These are U.S. because if you look at the metric units, you'd be. But good question because they're completely different. I put those up there just so single pane R1, most double pane are about R3, and then these. There's a lot of new manufacturers building U.2 to 0.22 for higher performance out there. You can build a passive house with that and meet it in this climate. You just have to build the walls a little thicker to compensate for not having as good of windows, but usually you want the windows somewhere around 0.15 or so. This is shown, I think it was in the 20s outside one day, and the guy who did the retrofit said, "Oh, my windows are frosting up. I wonder if that's bad." But really, it's just showing there's so little heat. The inside was still at about 68 degrees, outside in the 20s, and there's so little heat going through, it doesn't melt the outside or doesn't defrost the outside. So that just shows kind of how good these windows are. They frost up just like the car window because there's so little heat escaping. For the airtight construction, most people do an air barrier. You have to kind of show the whole house where you want the air barrier to be, from how it transitions from the walls up through the roof trusses and down through the ceiling, through the floor. So here they're just taping all the exterior sheeting to make that the air barrier, and then they'll seal the windows, and that's how they get the airtight construction. Before this, if you were just using a standard house, you wouldn't tape it, and that's where you get probably a leaky in the order of 4 to 5 ACH, where this one you're shooting for 0.6 or less. And this tape they've developed, and it's really sticky, sticks in even when it gets water on it and things. So they're building pretty good products now for this type for air sealing houses. Yeah.
Is it tongue roof?
No, this is just they actually use plywood. A lot of times, passive house doesn't focus on the sustainability of different products, where some builders will say, I don't want all that OSB with all that sealant, even though plywood has some, but they think it's a little bit more sustainable. But here it's just probably 1/2-inch plywood with the seams taped. Put this here just kind of show. This is that retrofit. When we started out, he was around 5 ACH, which is pretty common for a house. And that is also one thing about passive house. When you talk about the floor area, they use a term treated floor area, which subtracts the walls and everything. So if you have a 2,000 square foot home, the passive house program might deduct the walls and some of the ceiling or some of the staircase and some other things. So it might turn out to be 1,800 or 1,850 treated floor area. So when you divide that, you get, but anyway, so that's what that ACH number is based on, around 5. After the walls were sealed, they went down to 3.1. We tested it. We actually used the blower door from Dr. Saylor's lab up there. Green Building Research Lab has this. And then the biggest change was the ceiling. So that's where all the penetrations are for all the electrical boxes, for lights, fire alarms, plumbing penetrations for vent stacks. And there's nothing really solid except for the drywall. So you're just basically putting drywall up against it and mudding and taping it. So there's lots of air leakage in the ceiling. So that was the biggest improvement there. And then after the floor was sealed, I got down to 0.77. They've done some more work. They're still trying to get down to the 0.6, but they haven't tested for a while, so they're probably pretty close. This just kind of shows you want the ductwork, like we talked about, keeping any ductwork in the conditioned space. So before, this ductwork probably would have gone in the attic, but on a passive house and high-performance homes, you want to keep all the heating system inside, so any losses from it stay in the house, and you're not going into unconditioned attics and such. And this construction shows that they put OSB on the bottom of the trusses as their ceiling barrier. So normally you just put drywall up there, tape it, call it good, but you really can't seal that perfectly. So for this, they just took OSB sheets, put it on the deal, and then actually had a drop ceiling for all the electrical work and lights. And this shows the actual HRV ducting that goes through this 3-inch ducts going to the living room and such. So you can do all the distribution in the ceiling, and then they would put the drywall ceiling on top of this. And then above the OSB, would be 16 to 20 inches of cellulose blown in, or 24 inch.
What kind of material is your ducting made of?
It's made of high-density polyethylene, so same as like milk cartons, very hygienic, comes from Europe. It's a double wall, and it's flexible. So it's smooth on the inside, it's corrugated on the outside for bends. As far as the building costs and the heating system, so normally when you're using more energy, or when you're the building costs as you build using less energy keep going up, and at some point, as this shows, you eliminate the whole furnace system. So you get a drop in cost, so you're saving quite a few $1,000s of a traditional heating system and other systems. So that's why they try to get to this point of 15 kilowatt hours per square meter. Is that usually where that lands? You can get close, but it just helps drop the cost of the project. And then I just throw the example of that passive house, the retrofit that was 2,100 square feet. Initially, when it was built in 1998, it, of course, had an 80,000 BTU forced air gas heater system, central forced air, and a 25,000 BTU fireplace. So they were able to get rid of that and only use a 2.5 kilowatt electric heater. They're looking at doing a heat pump, but right at that time they only had money enough to put electric. So even though they're using electric, it's so much less than what they were, it still can pencil out. And you notice it's about 10% of what they used to use. Smaller houses, you hear about them saying you can heat a house with a hairdryer. Hairdryer's around 1,200 watts or so. So in some houses, 1,200 watts would heat the entire passive house. So that's kind of where that saying came from. So again, just to kind of reflect very low energy use. It's why I got also involved with it is when you're kind of researching things, you can look at trying, if you had a normal house envelope, you can try to get more efficient mechanical devices, the heating system. People talk about ground source heat pumps and fancy, expensive heating systems. But really, if you put the money into the walls, that's where you're going to get the most bang for the buck. So it is a very viable pathway to net zero, because once you put that money in the walls, you can reduce the size of any solar panel you need to get to net zero, where on a normal constructed house you need 10 times the size of a solar panel. Improve structure durability, so not only does the making it airtight help that you're controlling, where the heat and air are coming into the house and leaking out. It also prevents moisture intrusion into the walls. So inside the wall, you'll get to a point where there's a dew point, and when air in the wall hits the dew point, it'll deposit water, and over time, you'll probably get water in the walls, prematurely deteriorating them. So this design also helps the durability, is one of the aspects. So you'll have a house that definitely lasts at least 50 to 100 years versus, a lot of houses they say are putting up now, they won't be lasting too long, of the way they put them up, because you want to keep the moisture, especially in this environment, out of the walls and causing mold and mildew and other issues. The increased thermal comfort comes from the fact that, like I said, the interior temperature is pretty much constant inside from the exterior wall to the interior wall. And also, say that you lost energy or lost power. If the power went out in a house like this and it was probably freezing outside, it'd probably only lose about 1 degree a night, And even though your ventilation system goes off, you can crack a window, get enough ventilation even during that time. So there's more survivability in this type of house too. We'll talk more about the ventilation, but the indoor air quality, because you're getting all that fresh air, great indoor air quality. Another thing, except for the windows, there are available windows, but the current technology and materials are there to build these. Nothing, just a little bit a different construction. And like I said, the windows, there's not as many window suppliers as you would like. And one last thing, the occupant behavior doesn't have as much impact on the performance of the house as other designs, where they can't do too much. They can leave the windows open, but really, when you look at different houses and how occupant behavior really affects the energy use, there's less of that in this type of house. And there's some studies on the web showing that. And like I mentioned, a couple of the challenges, it does cost 10 to 15% more. This is just new construction, and that's mostly for the windows. A little bit added labor costs for the framing, and a little bit more insulation. The contractor, the framer, there's more attention to construction details for the airtightness, and limited U.S. window suppliers. Yes?
You discussed the walls in great detail. I'm just curious, what about the foundation, like the flooring, to keep it from sinking deep into the ground?
Yeah, so it depends. So people have built crawl spaces, basements, and slabs. A lot of the ones you see new construction might be slabs, where they actually will layer 3 layers of XPS, rigid foam, underneath the foundation, underneath the slab, and then actually wrap it around the side and really insulate all around the side. And they've got special structural permit, because the city says, hey, you don't want anything sliding when you have a loose layer, but they've done all the structural on that, and that's the way most people are doing it. Yeah, I guess I don't have any slides showing that, but so for a slab, that's what you do. For a crawl space or basement, for a basement you might use insulated concrete forms, and then go right into the house with rigid foam on the outside, so you have a nice continuous thermal barrier. But like I said, for most slabs, they're just using the 1 XPS that are built to take a load. Like I think in the pink board, it's the 250 requirement versus the 150 style. Yes?
You mentioned solar panels briefly, that you can take the money and put that in the passive house, and it's more effective to do that. So can that make it basically, are there any passive houses that are solar panel products?
Yeah, there's a few in California, especially because of their rebate systems. There are quite a few that want to get to net zero. But yeah, it's cheapest to reduce your energy load first, where you're putting the money into the walls, then putting it into solar panels. Even though now solar panels have probably reduced by half in the last 3 years or so. So now it's maybe getting close to break even, but the main thing is, as people say, the low-hanging fruit is putting the money into the walls and into more energy-efficient water heating and things like that. And then after you reduce all your loads that you can do it that way through energy efficiency, then look at what loads you have left for your solar. I don't know if that answered your question, but
So you're not looking for a net zero home, you're just looking for an energy efficient home. Is there an advantage to putting solar panels on?
no, but if you're trying to save as much energy as possible, it makes sense. A lot of people are trying to do carbon neutral, so this passive house planning package also looks at trying to find out what would that be, how much solar you have to put on to be carbon neutral also, because that's a concern for a lot of people too. They try to, yeah.
But we're just talking about PV, not solar hot water, right?
Right now PV, but
Well, just solar hot water is way more efficient.
yeah. And like I said, after you reduce the cost of heating the house, your next biggest cost is heating the hot water. A lot of people are, experimenting with or looking at the heat pump water heaters. Like in this duplex, there are 2 heat pump water heaters. But it really reduces the heat or the temperature in those rooms that they're sitting in. So they're looking at, helping using some of that cool air to cool the house in the summer. But it does, wherever you put that heat pump water heater is going to cool the immediate area unless you duct the cool air out. Because you're basically, you're taking the heat out of the air, putting it into the water, and then your exhaust air is much cooler as you go through that refrigeration cycle. So, all right. So anyway, back to ventilation. I was going to talk a little bit more. I don't know how much time left I have. A little bit. I'll keep going here. So it's there's a model: build tight, ventilate right. If you don't ventilate, this is type of problem. You get mold, mildew happening throughout your house. So if you just super insulate it to try to save energy, you're going to get problems like this. This graph, found this kind of interesting, that where our bodies are more comfortable at is a good place for them to be to prevent viruses and bacteria. Where, if they're wet, it might happen, but I didn't really know when it's dry. Like when you're in airplanes, there's also a problem, the air quality on airplanes and such, where you might be more susceptible to get bacteria and viruses, even though it's a dry air. So we're kind of programmed to be most comfortable at that, because when the humidity gets too hot, like on the East Coast, it's uncomfortable. When it gets too dry, your skin cracks and everything. So it kind of just helps to keep buildings, very control the humidity, so you're not getting too much or too less. In our ventilation strategy, we're adding the fresh air to the bedrooms and living room spaces, and then we're exhausting from the kitchen and bathrooms. So this would actually replace, in most areas, they're just, we'll talk about it later also, but the requirements for bathroom exhaust for code, to meet code, you can do a continuous bathroom ventilation instead of just the intermittent bath fan. So this is working 24 hours a day, just supply constant fresh air. And like I said, you're supplying there and you're taking out of the wet areas where fumes and exhaust fumes might happen. This is a system that's in that duplex and the other houses we talked about. It's kind of a combination hybrid where it's kind of going across in a counterflow, where air comes in here, goes across, and then out, and they pass. So it gets a little bit more efficient than other types. So to your question, heat recovery ventilation is you're recovering the heat energy when you're exhausting that heat, and it's coming across this heat exchanger. And inside the heat exchanger are very thin plates, so every other plate the air is flowing across. And there's around 340 square feet of surface area in there. So if you laid out all the plates, they'd put an area, almost 20 by 20 feet. So it's very dense, and that's where the efficiency comes from. Okay. And this is the one where it looks like, this is the one in No's house, as well as the retrofit, where efficiency is about 90%. Passive House Institute grades it a little differently at 3. It takes the average of 3 very low temperatures and then subtracts off the wattage. And then here we had it tested at HVI, tests a lot of bath fans. So if you go into their website, it kind of compares bath fans in one section and a lot of HRVs, ERVs on the other section. So on their tests, this was pulling in 32 watts on a medium speed, and the flow rate was 99 CFM. And then the max flow rate on this unit is 200, 206. And the 350 comes from 350 cubic meters per hour, which is the European metric system. Yeah.
Do you know the efficiency for getting that motor? By chance?
No, I just know it's the ECM, and this is the wattage. But so anyway, so the best efficiencies occur. We try to set it at about, when you're running continuous speed, about 50%. Somewhere 40 to 60% of maximum speed for the best electrical efficiency, and then you still have a boost button. So when you're in the bathroom or cooking quite a bit on the kitchen, you can go and boost the system up to level 3, which would be 30% higher, 30 to 40% higher. Yeah.
Do these operate differently in heating season and cooling season? Is there a changeover, or does it do the same thing the whole year?
It does the same thing. So the air, they don't change any of the ducting or passages inside. The air just comes in and passes. So if now the air, instead of coming in really cold and the other one's transferring heat to it, if it's coming in hot, and say it's coming in 95 degrees and you're exhausting at 70, 72 degrees, that 95 degree temperature will reduce to within 2 or 3 degrees above room temperature, so it'll be coming in at 75 instead of 95 degrees. So the heat exchanger, yeah, there's nothing, no changes to the system, and it just does that. Only air to air. Right. And our pretreatment system only does, like I said, below freezing. They do that, or you can have an electric preheater, but electric preheater uses about 800 watts, which is a lot more than the 50-watt circulation pump for that ground source system. But that's when it's below zero. But yeah.
Is it easy to retrofit everyone else?
Yeah, it depends on if you remove some of the drywall or feed it through. But the ducting, I don't think I have a picture, but it's a 3-inch ducting that you can just snake around. But there's different strategies for that. You can just get it to the bathrooms and kitchen, and then maybe feed it in to a couple spots in the house versus the entire house, or just do the upstairs bedrooms and bathroom where people are sleeping. I think that's any other question? Oh.
Yeah, so we're talking about heat recovery. Is there any benefit or anything you can do for the cooling side of things when you're in the cooling mode?
Yeah, actually, a couple slides down we'll talk about that. But the only other way to cool it is provide a cooling coil downstream. So then you got to watch about condensation. And if you use the earth to cool, you can probably the ground temperature around here might get up to 55 in the summer. So if you can cool it, you can cool the incoming air from 95 probably down to 60, 62, just using a loop, not a refrigeration cycle, but just circulating glycol in a ground loop, at least 3 to 4 feet below the earth. And however, if you get the air down to 60 degrees and the inside air is 75, you're only providing about 15 degrees delta of cooling, and these systems run about 60 to 100 CFM. So you're less than a kilowatt of cooling, or you're less than maybe you're maybe around 2,000 BTUs of cooling, which is negligible on a normal common house, but on a passive house that might be a third to half enough to cool it, or in our climate maybe that's enough to keep it cool. So there are some things, but it's tough to cool because you're dealing with such a low delta. And however, in the East Coast, it would really help to dehumidify. So when that 95 degree, 90% humidity air hits something that's 65 degrees, it'll condense a lot of the water out before it gets in the house and make the actual house feel cooler also. And then you'll hear about ERVs. And so on the East Coast, they use mainly ERVs. HRVs, you're only transferring the heat, so they're solid panels, little in the heat exchanger, where ERV, semi-permeable membrane, they're using similar technology to the same as fuel cells, but it actually allows moisture to pass through, usually about 60% of the moisture. So if you're in a hot, humid climate, it keeps 60% of that moisture outside. It doesn't transfer at all. So as if it's less humid inside, you don't want to be bringing 90% humid air back inside. So it's transferring some of that humidity to the exiting stream, but it still doesn't mix the flows. It's just allowing moisture, not the actual air. When I first started, I thought, most of the time you talk about really cold, dry air, and when you heat it up, it becomes even drier because cold air holds less moisture relative, for the relative humidity. So you would think Alaska would need an ERV because it wants to keep the moisture inside the house, but they're finding they're building so tight up there that they're using HRVs just because they have more of a moisture problem build up inside the house than problem with dry air getting in. So they're using HRVs in Alaska. So mostly ERVs are mostly just East Coast, Northeast, and places where it's hot and humid. So getting back to just a typical system layout of this just shows the actual yellow lines are return lines. They go back to an HRV down here. So it's coming from the bathroom and the kitchen area, and then the red lines are supplying to the living room and bedrooms. And then here, you just have a distribution box, so you have maybe 6 or 7 inch duct going up to a distribution box, then this 3-inch ducting will come out of it and run to all the other areas. So you can use conventional ducting, but most conventional ducting is made for conventional systems which are flowing 1,000 CFM for a central forced air system, where this is flowing 10% of that, or 100 CFM, 60 CFM. And then this photo also shows the ground loop where you're circulating water, just glycol, and it's going through just a hydronic coil, and the air is coming in and going through that before it enters the HRV. So those, like I said, that would be just for the freezing conditions. We talked about that, and then supplies. No, there is just a small pump, and it uses about 50 watts. So only when it's needed. And it's just circulating maybe 2 gallons a minute or something like that. It doesn't need much. It's just tempering. So there, like I said, no refrigeration cycle. It's just tempering the air. And you only have to temper 60 CFM of air. If you're in a smaller, compact type of house, they actually built systems that you can just drop, especially in a retrofit, you can just drop maybe the hallway. If the hallway's got some decent height, you can drop the hallway 12 inches or 10 inches. Fit all the system up there, and you can see it, go into the bedrooms, living room, and then exhaust out of the kitchen and bathroom. So that's used more in a retrofit application. And then usually most codes, you have to keep 10 feet separation with the intake air and your exhaust air. A few types of HRVs. This one's a cross flow. And this one would be maybe 65, 75% efficient. And where it loses, so say this is cold air coming in from the outside, say it's 40 degrees here, and say this is coming out from the house, so it's 70 degrees. The 70 degrees is cooling off as it goes across, and it might get down to, say, 50 degrees here. So it's losing 20 degrees, where this one might be increasing 20 degrees. But as this air is flowing across, you see that this air at 40 degrees only hits this air, or excuse me, hits this air at 50 degrees, and only picks up 50 degrees at maximum. And as it goes across, so this air that's transferring here is the only air that gets up to 70 degrees, because it's passing it here at the hottest, where this is cooling off. So on the cross flow, that's why you don't get quite as efficient, because it's about, like I said, 65 to 75%, because all the flow is not passing the entire flow of the other, going the other way. Where more of a counterflow is this way, so you pick up, maybe 15% more efficient system. And then there was a question about in the summer. So in the summer, in the evening, say it's 95 during the day, house gets maybe up to 75 during the day or so. And then at night, the air outside cools down to below room temperature, and you don't want to be keeping it. If the heat exchanger was going on and say your outside temperature was 60 degrees, it would actually be heating 60 degrees up to almost room temperature before it came in, which would keep your house hot. So this has automatic bypass where your exhaust air is bypassed around it. So if the outside air is 60 degrees and there's a call for cool, or it's saying, hey, the house is warmer than I want it to be, it'll open that bypass in the summer as the temperature outside drops and just bring in 60 degree air, 55 degree air, and it won't be much cooling, but it won't add to the heating load. And again, we're only talking about 60 CFM, a third of an air change. So during a night, if you have the windows open, you're going to get quite a few air changes during the night. 20 or 30, where this is only doing 1 inch air change every 3 hours. So at night, you'd only get 2 or 3 air changes. And usually most surfaces like drywall hold a lot of heat. So you got a lot of cooling load there to remove. But it's going to help. But the best is to open the windows and cool it off if you have that issue.
Has there been any automation incorporated to, like, when the house is fully empty, you just shut everything off and then, like an occupancy sensor or something like that?
It has automatic where you can program, like if normally people aren't home during the day, it'll drop down to level 1, like a 7-day, 24-hour program. But and then if you're on vacation, you press the vacation button, it drops down to 15%, and just so it turns over a little bit of air during the day to keep it somewhat fresh. But because it's using so little, they don't feel that you need to shut it off, because when it's only operating at 15%, so maybe 10 watts, it's like a 10-watt light bulb, so you're not using much, using only a couple cents a day to keep it going. But that's a good question. But there's a lot of commercial applications where you're having automatic window opening during evening to night flush and different scenarios like that. I'm sure you'll talk about more in this class. And then you'll hear about wheel ERVs. I'm not an expert on these. This just has a rotating wheel with transfer material, kind of like a sponge or a foam. And as it turns, the hot air will go, and then it'll move up, and the other air will turn, so it's continuously revolving and transferring heat that way. Most of these aren't PHI or Passive House certified because of the leakage. There is some cross leakage, so you have to look at that. But they can be just as efficient, but sometimes, like I said, there is a little leakage where you'll get some of the return air that stays in the media will be crossed to the supply area. And then we talked about a little bit about efficiency, but why this matters. If your system's 75% efficient or 60%, your incoming air will be, around 60. So in most systems, a lot of people are putting HRVs into your standard house with a central forced air. So then this air goes directly into the forced air system and gets heated or cooled. So that's not a problem when you're using a lower efficiency. You're still using a little more heat, but you're not feeling it. But then you're only getting fresh air when the whole central forced air system's running. So that big 1,000, 1,500 CFM fan's running, which is taking a lot of energy. That's the only time it distributes fresh air to the entire house. So in your shoulder seasons in the summer here, you're not running your HVAC system. So we usually put independent fresh air system in. But you kind of have to take a look at that. But a lot of HRVs are connected directly to your forced air system, and they're using less expensive units that are, have this efficiency. But since, like I said, you're not feeling the air. But if you're in a passive house where it's coming directly in, or say your floors are radiant floors, so you're not heating air, and you have air coming in at 60 degrees, you're going to feel cool, and you want to preheat that air. So that's why you always look at efficiency. And this is just a graph to show, this is on that passive house retrofit, but this just kind of shows what's happening with the temperatures. So this house, beginning of April, they weren't heating it at all, so they're just using solar heat gains and heat gains throughout the house. So no active heating system. And it's just showing that the HRV, temperature coming into the HRV, say this is at middle of the night, and then down here it comes in at 43, so kind of like the temperatures are now. Your temperature is around 43, so it's the same time of year at night. However, as it goes through the heat exchanger, it's warmed up to this temperature. And then the top line is showing the exhaust temperature coming from the bathroom. So it's a combination of bathroom and kitchen exhaust, where they're keeping the house about 68 degrees. And then that temperature, that airstream, then is cooled down here. So this is about 2 to 3 degrees, and that delta is 2 to 3 degrees. So that's where that 90%. So as you see the diurnal swings of the temperature, so this is over 5 days, the daily cycle, the house isn't changing much. It's changing maybe 1 to 2 degrees, but they're adding no heat, even though it's pretty cool at night and you're bringing in all that fresh air. So that's kind of how this, looking at it on a chart. Any questions on that, or kind of breezed over that pretty fast? But so anyway, so like I said, that's taking the temperature of the 4 ports. So on the HRV, there's 4 ports. One's this fresh air supply, and then that supply goes through the heat exchanger and goes to the house, to the rooms, bedrooms, and say the living room. And then the other 2 ports, it's the return air coming from the bathrooms and kitchen, going into the port and going through the heat exchanger, and then to the exhaust. So as you see, it's giving up the same amount of temperature, where the exhaust temperature is cooling down to within 2 to 3 degrees of outside temperature, and that same heat is being added on the inside. So the supply air is being increased from outside temperature to within 2 to 3 degrees of room temperature. If it was 100% efficient, the 2 lines would be the same. It would gather all the temperature. Just a quick efficiency equation. This is actually assuming both flows are balanced. We try to keep both flows balanced. So if you do that, and neglecting humidity. So of course, if you have humidity, like in the East Coast a lot, if you're trying to cool the air, most of your cooling goes in, doesn't decrease the air temperature, but it will cool the humidity and maybe condensate it out. So you can't use this. But this is just a very simplified efficiency equation where you're taking T2 minus T1 is the supply temperature minus the outside temperature. So that's the air. How hot did you warm that outside air up to? And that's this one. So say you warmed it up from 40 degrees up to 67. And then you divide that by T3 minus T1. So that's the return temperature minus the outside temperature. So that shows you that's 70 degrees minus 40. Or so that'd be 30 degrees. So you warmed it up 27 degrees. Am I doing that right? Yeah, 27 degrees divided by 30 is around almost 90% or somewhere in there. So that kind of shows you kind of the efficiency. Another thing we talked about a little bit is the heat content. This is, I think it should be 1.085, but this basically just tells you how much heat that airstream can carry. So a lot of people say, well, why can't you heat the house through the ventilation air? So then you got to look at how much that is. So if you take, so when you're heating it, your delta T, you can heat, say the air is coming in from the HRV at 65, and then you add a downstream heater to heat it up to about 120. So that's a 55-degree delta. At 60 CFM, or say 100 CFM, say you have a bigger house, maybe 2,500 square foot, and you need 100 CFM continuous. So that 55 times 100 is 5,500 BTUs times 1.08. So you're close to around 6,000 BTUs, and that's all the heat you can carry. So if your heating load is more than 6,000 BTUs, you won't be able to heat on that in the ventilation air. So there's very few times you can do that. You hear about people trying to, but if you bump up the airflow to get the heat to the house, you start overventilating the air, and if so you have to kind of look at, and then you have to make sure you're getting the air to the right place, and equalize it. So anyway, it's that formula comes in. Where also, when you're trying to cool the air, our early example where we just said, hey, you can get the temperature down to 60 degrees of the incoming air, and then your room temperature is 75, so you're supplying a 15-degree delta temperature into the house, times your 100 CFM would be 1,500 BTUs of cooling times 1.08, so you're still less than 2,000 BTUs of cooling you can supply over this air. So you will get people asking about heating and cooling over the ventilation air. So it's not too often done. Some people do it, but you have to be pretty careful with how you do it. And let's see. And then this 1.08 just comes from taking a specific heat of air, timesing your density, and then that give you pounds, and then to convert, and then CFM, and then timesing from minutes to hours is 60. So if you take 60 times 0.24 times 0.075, you should get that factor of 1.08. Any questions on that? I figured I had to put a few formulas in since this was an engineering class. ASHRAE 62.2, people familiar with that? It's kind of one of the ventilation codes people use. So it's just saying in a residential, it's 62.2. Supply air equals, this AF is the area of the floor rate, and NBR is number of bedrooms. So it's saying in a house, you need to have this much minimum supply air to keep it healthy. So if you multiply that out, I did an example of 2,000 square feet. So it'd be 0.01 times 2,000. And if it's a 3-bedroom house, that plus 1 assumes there's 2 people in 1 bedroom. So there's 2 people in a master bedroom plus 2 other bedrooms with 1 person. So it assumes 4 people, and then they assume 7.5 CFM of fresh air per person, and then a little bit extra for the square footage. So it comes out to, in this example, the minimum would be 50 CFM of constantly supplied fresh air, and that's what the building department makes sure it has. And that equals, for this example, that'd be an air change rate of 0.19. If you do 50 CFM and look at your volume of air, you're getting an air change rate of about a fifth of the air change an hour. And then briefly talked about before, trying to change that to say what would it be at ACH 50. So that kind of shows 0.19 is a minimum required in this house, and that relates to about a 0.38 air change per 50. Like I said, that's about an average. You can go higher or lower depending on if you have a higher building or more wind exposure. But it's just saying if you're below or actually, it should be 3.8. I think is that right? 0.19 times 20, 3.8. So that's my typo. Excuse me on that. So it's just saying if you have a house that's less than 4 air changes per hour at 50, you start getting less than the required amount of natural ventilation. So most houses in the past have been above 5 air changes per hour. You didn't have to really worry. But once you get below 4, you can't really rely on natural ventilation giving you the required amount. So that's why, like, even 3 or so. So, yeah, so I'll have to fix that typo. So just a FYI. And that's the minimum. And then for exhaust, that's supply air. Then exhaust air, they talk about continuous is 20 CFM per kitchens and 5 air changes per hour based on the kitchen area is ASHRAE 62.2. So it says you can either do continuous or intermittent. And most common houses now do intermittent. Most stock homes, you have a bathroom fan that blows at least 50 CFM and kitchen fans that blow at least 100. Yeah.
So I know we talked about like CFM before of the heat recovery ventilators.
Right.
Do you know approximately what the ACH is with those on?
Yeah, we try to just set the continuous for 0.3 air changes per hour.
Okay.
Yeah.
And then so if you were to do that modification, it would go up to like 5 or 6.
Yeah, unless you're.
With that active heat.
Yeah, it would go from 0.3 plus whatever your natural is. So, but also if you slightly positive pressurize the house, it'll reduce the amount of infiltration too. So, but anyway, yeah. So you have your choice per the code. Different building departments will have different though. For example, the state. If you look at the different states, Washington, Oregon, California. In Washington, bathrooms are 20, and then the kitchens are 25 for continuous. Which is, I think, from the International Building Code, which deviates from the ASHRAE. So there's different codes out there. Some building departments follow ASHRAE, some, changed it a little bit. Oregon just changed theirs. There's before last summer, it was 20 and 25, and now they said, hey, we don't want continuous, we want intermittent only. So, so there they say, hey, you need to have a direct exhaust vent on your kitchen that vents 150 CFM. That was a new change. And then in California, they're using exactly this ASHRAE of 20 CFM, and then kitchens, they need an exhaust rate of 5 ACH. So when you figure this all out, usually the exhaust rate dictates the system design. So, and then in a passive house, the exhaust, bathroom 24, kitchens 35. So when you're designing in Washington, you just design for passive house and you meet this, and that's all. But with Washington or with California, Oregon, you have to do some more to look at that. And then passive house supply is just 18 CFM per person. So back to that case of 2,000 square foot house, 3 bedroom, 2 bath. For 4 people, that'd be just less than, what's the number on that? 72? Did I do that right? 72. And then the other one's about 83 or so. So in that case, the exhaust would dictate. You design the exhaust for continuous of around 83, 85 CFM, and then you meet passive house. And then you also check to see if that's around 0.3 ACH, and then that's kind of your design. So might be running a little over here. And then the last thing I had was a couple slides just on comparing energy use of using bath fans versus HRVs. So if you say 0.3 is 60 CFM, and you compare just running a bath fan, this one shows just running a bath fan continuously to get your air exchange rate. You would use, you bring in cold air, so you need 62,000 BTUs per day to warm up that. So that's if you just turn that bath fan on, you're exhausting that much air, and you're having to bring that makeup air and heat it up with 62,000 BTUs per day. If you just do 2 bath fans for 120 for 2 hours a day, which is pretty common, that brings in 14,000 cubic feet per day. and uses 10,000 BTUs. However, this doesn't meet your air changes on a tight house, but it just kind of shows you the difference. And the makeup air temperature is coming in at 30. So if you have a 75% efficient HRV running 60 CFM continuous, you're still getting the 86 cubic feet per day, 86,000, which meets your requirement. But you're only having to use 15,000 to heat it versus the 62 if you weren't using HRV and pulling the same flow rate in. And your makeup temperature is 60 degrees, and that's why. And then if you go up to 90%, you drop from 15,000 BTUs for heating the makeup air down to 6,000. So it kind of just gives you an example of the old way of just using the exhaust fan. But as houses get tighter and tighter, you need to make sure you get at least 0.2 air changes, which is ASHRAE, the 0.2 air changes. You prefer 0.3 air changes, and to get that takes a lot of makeup air. So the HRV helps you prevent having to heat it. Heats it for using the exhaust air. I think that's all I had. That was pretty quick, but oh, you had a question?
It seems like you developed a method to make a pretty tight structure. So that probably the weakest link is the fenestration.
Yeah, yeah.
So the goal really there is passive house design.
Yeah, but the other thing is they're so costly. They're the payback on and trying to get cost-effective, high-quality windows. Which the one time I went to Europe a couple times, you'd have medium-priced hotels that would have these really expensive tilt and turns because they are much cheaper over there. It's just that there's not as many suppliers building them here, so you have to ship everything from there. So once, like I said, because the energy prices here are so low, it doesn't benefit, it doesn't promote these energy savings windows. People supplying them here, they're starting to. So as it becomes more common, I think I heard California building code for residential was trying to get net zero by 2020. So they're trying to say, hey, we're going to increase the building codes to dictate or to mandate building towards net zero by 2020. So that'll, as California sometimes leads the way in building codes, and Oregon and such.
So you mentioned the passive house planning package
Yeah.
briefly, but you didn't really get into it much. Can you comment just a little bit on the availability of it in terms of whether it's freely downloadable and then the level of sophistication needed to run it as
Right.
say a student in a class like this?
Yeah. I didn't quite get in it because you could spend quite a few hours discussing it. But basically, it's Excel-based. So just picture an Excel spreadsheet with many tabs below, like a ventilation tab, a Windows tab where you enter the windows, and it does, it does an energy balance, and then it has some correction factors, but it's based on empirical. It also was, first done, and then it was checked against empirical data they got from the field. But it is, I think it's available $300 or so.
Did you put in your localized weather file, that kind of thing?
Yeah, it has files available in their format, but it's basically that. It has Portland and Seattle built in, so those are all available. The main thing, they do offer training, 2 or 3 days training, because there are some tricks. Because it is a spreadsheet, you kind of have to know your way around it. So they kind of have also books for about the same price to actually go more detailed instruction manuals for it. But the class is also good because, like I said, it helps you navigate it and make sure you're filling out everything and not forgetting to change something. So they really look at thermal bridging, these psi values, PSI for the Greek letter, for thermal bridging and windows and that type of thing. So they even say that they've corrected that the amount of water, say when your toilet fills with water, the amount of heat that you're lost when you flush it, on the average of how much heat is lost through water. So they say they actually look at how much heat loss is in the building. they've nailed it really down. And the Germans are pretty, good detailed people, so they get it pretty detailed. But it's available. It's not that expensive, but it would take a while to learn if you're going through the first time. And
is that what your company uses for those parts, or do you have more detailed than that?
My company just does the ventilation, so we just take what they request or kind of understanding what they need, and just have them send us your ventilation page, or tell us what your continuous ventilation requirement is from that, and then we compare it to the code and our design criteria.
So you're on like the design criteria of the piece itself, it's sort of being installed.
Yeah, how much CFM is going through each tube or to each room.
So these are custom designed, like one design here, one design here. There's not just like off the shelf.
No, but they're pretty common, so it's not too different. Most full baths take the same amount of flow, and so you can base it on square feet and everything.
What's the advantage of the intermittent fan compared to the continuous? Like, why wouldn't you just want a continuous, just kind of adjust the flow rate for the air so it matches
Yeah, so when you have a loose house, as most houses were, and the fan motor technology wasn't as good, so basically price also. So you got cheaper intermittent fan motors that take more energy, but you're only running them for a short time, and they're pretty noisy, and the continuous ones, you want to reduce the amount of energy. So they are ECM motors, which are quite a bit more cost, but very efficient. So it's just, like I said, in the past, with looser built houses, you didn't need continuous ventilation. But as I was trying to show, that under about 4 ACH, 3 and 2, especially under 2, you definitely need some balanced, what you would call balanced mechanical ventilation, where you bring as much supply in as is exhaust. Yeah.
What, as like a certified passive house consultant, I mean, you've got a certification, but then you work for vendors, so like you.
Yeah, I'm kind of not common there. So most people would be in the business of either an architect that wasn't. They'd say, hey, I need you to help with this passive house, do this. If we're building a passive house, do this part of the calculation, give it to me. Or if some homeowner says, hey, I want to go build a passive house, they'd hire you as a consultant. It just helps me working for Zender because probably half the projects we do are passive house or net zero. So it just helps me understand what they're looking for. And most people that went through the passive house training were probably architects. Probably half were architects, some builders, and then some engineers. So it's probably only 10 to 20% mechanical engineers and at least 50% architects, I would think. And so if you look up passive house consultant, you'd find mostly architects because it's just another part of their building or business they can offer their client.
And where are most of these being installed, geographically speaking?
A lot on the West Coast, Bay Area here for HRVs. You're talking, right? Yeah. So, like I said, we know Portland's really green. Seattle is doing a lot of high energy, high efficiency buildings, and then the Bay Area are doing mostly net zero, but passive houses, especially because of the solar. They have more solar resources, plus more solar incentives from the state. But a lot along the West Coast and a lot on the East Coast and everywhere in between. But most of the new covering, we get a lot from Utah and all over Midwest, Chicago. But generally, by the time you get down to LA, you don't have as much heating load, so it's not as much as cost effective in sunnier climates.
Do you guys get any trust incentives, or do you get them to your customers?
They're looking at getting qualified for that. So.
And that varies from state to state.
Right. So it's just Oregon really doing that. Vermont, I think, gives some, and some of the East Coast, I think it's Vermont, Massachusetts, have some good rebates.
Do you see this mostly new construction or is it retrofitting?
Like I said, retrofitting costs more, so we don't see it as much. But they're able to do it. So if somebody likes their house and just wants to upgrade it for the future, like this retrofit, he nicknamed it the Future Fit. So he was retrofitting for the future. But it's mostly in new construction, and it's becoming more mainstream. You'll see it in the fine home building magazines. They'll do quite a few articles. There's quite a few articles online. But like I said, it's not the only one. There's other building, design standards. Like I said, there's one called Minergy, Minimum Energy, that's out of Switzerland. There's another one called Active House. That's focused more sustainable practices. There's a Living Building Challenge from the GBC, just like LEED. LEED's good, it's focused on sustainability, but it doesn't quite get the energy. Doesn't say, hey, you must meet this energy requirement. You can make kind of a looser energy house, but more sustainable. But I guess that's it.
One last question.
Hopefully. Yeah, and Professor Saylor has my contact information. I didn't write it here, but if you have any other questions, you can get in touch with me.
Well, will this presentation be available to us?
Yeah, I got to send him a PDF of it, and then he can put it online.
Thanks, Matt.
All right.